Hello, everyone. Thank you for joining me today. My name is Henry Toal. I am a researcher at the Alaska Center for Energy and Power, which is a applied research group based out of the University of Alaska Fairbanks. I am here to give you an introduction to solar energy performance modeling in Alaska. And this is part of a larger effort that we are calling the Microgrids in Alaska Group Photovoltaic Integration, or MAGPI program, which is a collaborative effort to bring together best practices, insights, lessons learned, that kind of thing from various stakeholders and project partners that have experience installing solar and battery energy storage systems across rural Alaska and help those partners develop new, more successful solar and battery systems moving forward based on existing knowledge. So today I'm going to focus mainly on the solar energy modeling part. I'm going to give you a brief overview of why solar energy modeling can be very valuable in these situations where you want to get a sense of predicted solar performance. I am going to talk to you a little bit about some of the options that are available to you for Alaskan solar performance modeling. And then I'm going to walk you through a demo modeling a system in Kotzebue, Alaska, where we'll take a look at the step-by-step process of gathering weather data from publicly available resources, integrating that with system information about the site itself, running our model, and then doing some analysis on our output to make sure that we've generated some believable, useful results. So let's go ahead and get started. So, really quick, let's just talk about why solar performance modeling can be really valuable. In simple terms, solar modeling is really just developing a system for predicting the expected power output of a given solar array. And so, really, you're going to need two primary things in order to do that. You're going to need some weather data. Solar panels produce power based on the amount of sunlight hitting them. Their power output is also influenced by things like air temperature, the specific type of solar module being used, the electrical interconnections, inverter model, all kinds of things. And the output of these models can be used at all stages of a solar project's lifetime. It's very valuable at the beginning of a project when system sizing is very important and we want to get a sense of how much solar a specific community might be able to utilize. It's very valuable during the commissioning process where you want to get a sense of your theoretical maximum or your theoretical expected output for a given system, and maybe you're not seeing that during the commissioning process, so it can be very useful to have that sort of baseline performance. And then it can be really useful for long-term performance assessments. So over the course of multiple years, are you seeing degradation due to just the natural degradation in panel performance, or maybe losses due to panel soiling, either from dirt or snow or other sources? And it can give you a sense of where your system is in terms of the long term expected performance. And so the actual steps to go from just some weather data and some basic info about your expected site to modeled AC system power is pretty simple. The chain of modeling steps you can see here, we start out with some weather data, the most important being what's called solar irradiance, which is essentially just the amount of sunlight at a specific wavelength that solar panels absorb. Um, that is then converted through some simple math into an estimate of how much sunlight is actually falling on the panel surface. Then we take into account any sources of shading, either from obstacles or other solar panels. Can be a major source of shading, which can reduce direct sunlight. Once we have all of that, that's passed into an electrical model, which converts the estimated sunlight minus the shading into some actual modeled DC power. And then, of course, a solar array wouldn't be complete without an inverter to convert that DC power into AC power that can be used on the grid. And so we also want to have an electrical model for our inverter to get our final AC output. Luckily, we don't actually need to do any of this ourselves because there are a number of both paid and open source tools which wrap all of this up into a neat, easy to use user interface. Um, the one that we're going to be using today is the System Advisor Model, which is a free open source tool published by the US National Renewable Energy Laboratory. And we're going to be getting our weather data for that model from another NREL product, the National Solar Radiation Database, or the NSRDB. And this is a particularly timely video because the National Solar Radiation Database recently expanded its coverage to include all of Alaska. So previously it only had data up to 60 degrees north, but now anywhere in Alaska you can get some high quality estimates of solar radiation, temperature, wind speed, direction, snow cover, that kind of thing. So it's really made the process of solar performance modeling a whole lot easier, and I'm going to walk you through those steps. So first, I wanted to quickly show you guys the NSRDB, National Solar Radiation Database data viewer, which you can find here at nsrdb.nrel.gov/data viewer. Um, we actually don't need to get our data directly from here because the System Advisor Model, or SAM, actually has this data set directly integrated into it. But I wanted to show you just how easy it is to get weather data from this data source if you haven't in the past. So these overlapping shapes right here just show the extent of different data sets. We can actually go ahead and zoom in here to Alaska, and we can see that for any given location, there's this new um, Arctic 2013 to 2023 60-minute 4 kilometers. And so what that means is anywhere where this data set exists, you can get hourly data. So one measurement every 60 minutes for the entire period of 2013 to 2023 in a 4 kilometer grid. So you can see here, if we zoom in on the Anchorage area, you can see that the area around here is a little jagged. That represents the rough grid size that we're working with here. So every date, all the data within these little grid squares is going to be the same, but it's still a pretty vast improvement over the data quality that we had before. So this allows you to get a pretty granular view of what the weather might be like at your specific site. And we can see that we have three options here. We have spectral on demand polar. We're not really concerned with that. That's more of for a meteorological application looking at the different wavelengths of light in different ratios. We have the historic data set from 2013 to 2023, so we could actually download all of that if we want. But and we also have the typical meteorological year, which I'll talk about this a little bit more in depth later. But what this is essentially a representative year of data that, using algorithms, has been cobbled together from multiple other years to give a statistically average sense of what the weather over the course of a year is likely to be in any given location. So these typical meteorological years are generated for each one of these 4 kilometer grid squares. And if we look down here, we can actually see all of the different data fields that we have. We have some typical ones like temperature, dew point, pressure, wind speed, wind direction, that kind of thing. We also have our irradiance measurements. So GHI here stands for global horizontal irradiance, etc. But if we want to, we can just go ahead and select all. Select our typical meteorological year, convert to local time if we want, type in an email address and click download, and you'll be emailed a link to collect your data. It's as simple as that. If you are more programmatically inclined, there are some resources here about how to access this data using the NREL API, but we're not going to go into that right now. And in fact, we're not going to bother with doing this manually because we're simply going to pop over into SAM, the NREL System Advisor Model, and let it do all this hard work for us. So, first things first, we're going to download the NREL System Advisor Model, or SAM. The download process is pretty easy, like any other open source software you might have. We have a version history down here, but we just want to go ahead and download the latest version. We have some introductory videos to SAM, some help files, PDF of the help files, and release notes. We're just going to go ahead and install SAM for Windows because that's the machine that I'm on, but we also have it for Mac and Linux if you are so inclined. So I'm going to go ahead and run the installer for SAM. Choose an installation point. I already have a copy of SAM installed, so it's noticing that, but I'm just going to go and click install, and it shouldn't take more than a few minutes to get all of the system files installed. All right, looks like SAM has installed successfully. I'm going to go ahead and launch, and here we are in the main SAM menu. Now, for those of you who didn't previously have a copy of SAM on their computer, you will be prompted to register your copy of SAM with NREL. This is totally free and takes like 2 minutes, but the reason that they want you to register is so that they can keep track of how many users they have on their system, because it's very useful to be able to report back to the government when you're asking for more funding, to be able to say, we have this many tens of thousands of people using SAM. And I happen to know it's quite a few. So, the way you'll do this is you'll be prompted to enter an email address in right here and then click register. I already have my registration key right here, but this will send an email over to your inbox. And that registration email will look a little something like this. You can copy your key from right here, go back to SAM, paste it in there, hit confirm, click OK, and you're all set to go. So, now that we have SAM installed, let's get started. Really quick before we get started, I want to talk a little bit about the system that we're going to be modeling today. So, this is the solar array in Kotzebue, Alaska, operated by the Kotzebue Electric Association, or KEA. It is at least this section of it, split into 8 different subarrays, is a 532 kilowatt array. Like I said, broken up into 8 sections. And if we pop on over to Kotzebue in Google Maps, we can see the main community over here, and a few miles to the south, the KEA solar array phase 1. So we can see here that it's broken up into 8 distinct subarrays. And so what we're going to be modeling is this whole array right here. 8 subarrays for a total of 532 kilowatts. So let's pop back over to SAM and get started. So back in SAM, we have the main menu right here, and we're going to go and we are going to start a new project. Now, SAM actually has a whole bunch of other functionality for modeling renewable energy systems, but we are not going to focus on any of that right now. Instead, we're just going to go to the top, photovoltaic or solar. We are going to select the detailed PV model because we do have enough information on this site to get pretty in-depth here. And then we can see here that it gives us some options for economic calculations. So SAM has a built-in economics calculator to calculate cost of energy, things like that. But for now, since we're just focusing on performance, we're going to select no financial model, and we're going to hit OK. And that is going to bring us into the first of the SAM model menus. So up here at the top, we can see that we have this tab called Untitled. That is our current project tab. I'm going to go ahead and rename this. Let's call it Kotzebue Tutorial. And right away, there's a whole bunch of stuff on screen right now. The thing about SAM is that it doesn't have a nice 3D viewer. It's all kind of done through this text-based interface, which I think we'll come to see actually works pretty well. So what we're looking at right here, the first tab that we have over here on the left is location and resource. So this, if we go back and we look at our modeling flow, is our weather data. We've got to get ourselves some weather data. Now, SAM comes with a few locations automatically installed. We can see that these are from the NSRDB. But we are interested in Kotzebue, Alaska. So, how are we going to get it? Well, we're going to scroll down here to this Download Weather Files tab. We do have the option to just search directly here, but this can sometimes get a little confused. So I'm going to go over here to this advanced download, and we're going to go ahead and click this download button right here. In this location, I'm going to go ahead and type in Kotzebue, Alaska. And there we go. It's as easy as that. So we have all of our yearly data sets, but we also have our TMY updated in 2023, and a few other files. I am going to go ahead and select just the base typical meteorological year file. I'm going to click OK. Oops, forgot to hit the checkbox. There we go. And then hit OK. This sometimes takes a few minutes. And bingo, there we have it. And so we can see that this menu up here has updated with Kotzebue, Alaska. So we've got this data file. Well, what does it look like? Well, if we scroll down here, we can see that it's got some summary statistics for our solar source. So our global horizontal irradiance, which is just the total amount of sunlight hitting a flat plane facing straight up in kilowatt hours per meter squared per day. We've got our direct normal, or our beam irradiance. So this is just the light coming directly off the sun. And then we've got our diffuse horizontal irradiance, which is everything else. So all of the light being reflected from the ground or off of clouds or off of nearby objects. We've got our average yearly temperature, our average wind speed, and also some summary statistics about ground albedo, which is the reflectance off of the ground, usually due to things like snow. So let's go ahead and view our data. So one of the very nice things about SAM is it has this very nice data viewer. We can look here at hourly plots of our beam irradiance, so our direct. We can also add other fields to that. And what's really quite special, so we can go ahead and we can actually have two different plots going at the same time. And if we click and drag over a section of that, we can actually zoom in. So if we want to say get a sense just of April, which tends to be a nice sunny month in Kotzebue, yeah. See, we have a lot of direct irradiance. Let's go ahead and turn off beam diffuse. Let's just do global horizontal. Yeah, very sunny. And then down here, let's plot albedo. We can see that the reflectivity of the ground is pretty close to 1, which is what we would expect. So still a lot of snow on the ground. If we hold control and move our mouse, we can zoom back out again, and we can see here pretty much what we would expect. May, things start to melt, and by early mid-June, we don't really have any reflectivity due to the snow, and then in late October, it starts to pick up again. We can also see some other fields here. We have our air pressure. No data for snow depth in this data set, it looks like, but we also have wind speed, wind direction, dry bulb temperature in degrees Celsius. Looks about right. And if we want to, we can get some monthly summaries, a heat map. So this is month and hour of day. Could be very useful. And we could get some general summary statistics if we'd like. All right, now that we have taken a look at our weather data for Kotzebue, let's go ahead and look at the second menu over here on the left-hand side, the module menu. So, again, a bunch of information gets thrown at you here right away, but let's go ahead and take a look at this one section at a time. Up here at the very top, there's this drop down menu that gives us some options for which model we want to use to simulate our solar panels. So, up here at the top, we have a very simple, bare bones model that lets you do a quick and dirty estimate. Um, if you don't have a lot of details on the specific module that you want to use. There's also this model created by Sandia National Labs and a more advanced single diode option for if you really want to get some granular details on how your specific solar module might be performing. But for right now, we're just going to take a look at these two options, the CEC or California Electric Commission Performance Model. We have two options for that model. We have the module database, which is a very, very handy feature presented in SAM, which is this database assembled by the California Electric Commission that has the manufacturer, um, specific model name, and performance characteristics as presented on the specific solar module specification sheet for hundreds. I mean, there's a wide, wide variety of very popular modules here to choose from. So you can search within this database to find your specific module, or if the database doesn't have your specific module, you can go up here to the CEC performance model with user entered specifications, and you can pull up the spec sheet for your specific module and enter in all of the data yourself and even change the name. Now, I happen to know that Kotzebue Electric Association used these LG 400 N2T J5 bifacial monocrystalline solar panels for the array that we're going to be modeling today. So, if we scroll down here on the LG website, we can see the spec sheet for this module right here. Now, if we pop over into SAM and we go over and we look at the CEC performance database and we search up LG 400 N2T J5, well, hey, look at that. It's right there. Now, it's very important that we take a look at all of these performance characteristics and make sure they match the values that we're seeing on the spec sheets. So we can pop back over here and confirm. The main ones that we're interested in are maximum power point current, maximum power point voltage, maximum power in general, short circuit current, and open circuit voltage, as well as this value right here, the bifaciality coefficient, and overall module efficiency. We also want to pay particularly close attention to these values right here, the temperature characteristics, which lets us know how this specific solar module will change its behavior at different ambient temperatures. So, back in SAM, once we've confirmed that all of this is correct, we want to make sure that this box right here is selected. So module is bifacial is very, very important to make sure that that box is selected if you are using a bifacial module and not selected if you are using a monofacial module, because the solar panels that can collect sunlight on their backside are going to produce a lot more power, especially when there's a lot of snow on the ground during spring. So we want to make sure that whichever type of module we're using, in this case, it is indeed a bifacial solar panel. Because it's a bifacial solar panel, we are going to be using this option. So we can go ahead and scroll down and look at some of the advanced options on the module tab right here. We're not going to change anything about the temperature correction options. Generally, this isn't going to impact these sort of first pass models too much. We're going to have it listed as a ground or rack mounted system. There are some options for building integrated systems as well, and one story building height or lower, which is correct. And then all of these values right here are automatically calculated. You can tell that SAM is automatically calculating a value or it's not changeable by these values highlighted in blue. So now that we have everything set for the module page, let's go over to the inverter page and do the same thing for our inverter. Now, likewise with the solar modules, I happen to know that Kotzebue Electric used these Solar Edge three-phase 600 or 66.6 kilowatt inverters. So let's go ahead and enter the data for these, which we can find in the spec sheet here, into SAM. And likewise with the modules, the inverter page has some options in this drop-down menu up here. We have, again, California Electric Commission database of inverters. We have a calculator for entering in various specifications about the specific state of the load in order to get more granular data, but we're not going to worry about that right now. We also have the option to enter in data from the datasheet directly, but I'm going to go over here. And if we just type in SE 66.6, there we go. Solar Edge Technologies SE 66.6 KUS. And so, like we did with our modules, it's always good to go ahead and take a look at our datasheet parameters right here to make sure they're matching up with what we're seeing from the published information from the manufacturer. And I'm actually glad that I double checked because it looks like the information for this inverter that's available in the CEC database is actually slightly different from the published information provided by the manufacturer. So I just went ahead and updated everything on this page to match up with the published information from the datasheet. And for the system losses, I just left it at the SAM suggested value of 530 watts DC. So now that we have everything set up for the inverter model, we can go over here to the System Design tab on the left-hand menu and get everything set up for our system electrical configuration. Okay, so over on the System Design page, we have a bunch of different options that we can use to configure our array for modeling. The first panel that we have up here is our AC sizing. And so the main value that we can change here is the number of inverters. As I mentioned before, the Kotzebue Phase 1 array has 8 of the inverters that we defined over on the inverter tab. So we can go ahead and enter that quantity in there. And we can see that a bunch of things get calculated automatically, but we're still way out of whack in terms of our DC to AC ratio, name capacity, and all that. And that's because these values down here haven't been updated. So there's two values that we can enter in here. There's the modules per string in subarray and the string arrays in parallel in subarray. And an important caveat with SAM is that subarray in this case doesn't actually mean, say, like the individual string plus inverter subsections that you might have in the actual physical system, but it's more of a way for SAM to be able to model different array configurations all in the same model. So if we were to say, enable these subarrays 2 through 4, we can see down here where we're able to define the tilt angle and the ground coverage ratio and the azimuth angle, that we could vary a portion of the array independently of the other portions. But because the Kotzebue phase 1 array is all the same tilt angle, all facing the same direction, we're just going to have one subarray defined for the entire model that we're creating right here. And so for the electrical configuration, we're going to go ahead and update that based on the parameters of the Kotzebue array. So the Kotzebue array has 20 modules per string. So this is strings of modules connected in series. And then there are a total of 72 strings in the Kotzebue subarray. And so we can see that the number of modules is calculated automatically from these two values. So 20 times 72 is 140. The open circuit voltage for the modules per string is just the defined open circuit voltage in the module page for the specific modules that we picked. So this value right here multiplied by the number of modules in series. And so that gives you this value right here, which should always be lower than our maximum DC voltage defined under the inverter. And then if we go over here, we can see that this value, the maximum power point voltage, is also automatically calculated. If we scroll down here to the tracking and orientations pane, we can see that there's options for different tracking and tilt options, but the Kotzebue array is just a simple fixed tilt system, so we're going to leave it like that. We're going to go ahead and update this to 30, which is the tilt angle of the Kotzebue array. Its azimuth facing exactly due south, which we can see over in this helpful little diagram right here. So 180 degrees is equivalent to due south. Kotzebue has a very low ground coverage ratio of 0.05. And the way that we calculate that, actually, if we go over to this shading and layout tab real fast, there's actually a very helpful diagram showing how to calculate GCR, or ground coverage ratio. And so basically, it's just the length of the rows divided by the total height of the array. So because our system, the system for Kotzebue is 2 panels high in portrait, it's just 2 times the length of one of the panels divided by the total row spacing, which in this case works out to 0.05. There are some other options down here if you're doing a more advanced financial calculation, where you can enter in land area values and it will calculate these automatically if you're incorporating land costs into your economic model. But since we're not doing any economic calculations, we're not going to worry about that. And then there's also a PV subarray mismatch, which is a more advanced set of calculations if you're using these subarray options right here. All right, so now that we have everything set up under the system design page, we can go to the next page on the left-hand menu, which is shading and layout. And this is where we're going to be able to calculate any losses in expected production due to shading, both from external sources as well as self shading from the modules themselves. And so this first section up here is the external shading portion. Sam does provide this 3D shading calculator that lets you create a number of different shading obstacles, and then calculate how those obstructions will impact your performance. So you can see that you can create various basic shapes, and you can go in here and edit where these are relative to your solar array. We're actually not going to use this for this particular array, partially because it's actually kind of finicky to use. And also, it's generally unnecessary for the majority of arrays that we would be modeling in Alaska. Generally, any place that has a large open field and there aren't any large buildings or other structures really close to the array, then just calculating self shading is going to be plenty. So we're going to go ahead and close this for now. Down here is the next section, which is the self shading section. For the type of self shading that we're going to be doing, we're going to select standard nonlinear. And then this section right here is the actual dimensions of the individual array components, which will allow Sam to calculate the size and shape of the array and thus what kind of shading it's going to be casting on the rows behind it. So if we take a look at the actual Kotzebue array, we can see that the modules are set up in a two high portrait configuration. So we can see that they're set up with the long edge of the module facing up, stacked too high. So this is two portrait. If we go back to SAM, we can make sure that our module orientation is set to portrait. The number of modules along the side of the row is 2, like we just mentioned, and the number of modules along the bottom of the row is 180. And so where we're getting these numbers, if we go ahead and we look at the Google Maps image of the Kotzebue array again, so we're essentially saying that each one of these whole sections right here is a row. So each one of these array portions right here are 2 high and 90 long. And so that gives a total of 180 modules in each of these sections. And so, but obviously, this array isn't casting any shadows on this portion right here. So, what we're essentially saying is that this is a row, this is a row, this is a row, and this is a row. And so, if we go back to SAM and we enter this in as 180 modules along the bottom, we can see that all of these values that are automatically calculated come out correctly. So, SAM is calculating that there's a total of 4 rows with 1,440 modules, which is the correct number of modules, and based on the Google Maps images, 4 total rows. And so the last section in the shading and layout page is the snow losses option. This weather file doesn't have snow depth information, but if you do have snow depth information, you can calculate the estimated losses from snow by checking this box right here, and it will use a rudimentary snow loss model to estimate when there will be snow cover on the modules and what kind of impact that will have on total array production. But since we don't have snow depth data for this weather file in particular, we're going to go ahead and skip that. And finally, we're going to come down to the losses tab under the left-hand menu here. And this is where we can input any expected losses in production due to things like soiling, so dirt or snow or other obstructions shading the front or rear portions of the panels. And then any losses due to electrical interconnections, both on the DC and AC side. So under this first section here, which is irradiance losses, we can enter in soiling on an annual basis, both for the front and rear side of the array, as well as the bifacial rack shading. So if we click here, we can actually see that we can individually change the expected percentage reduction in irradiance due to soiling. So say if you didn't have a good sense of what your losses due to soiling or snow would be in any given month, you could go ahead and say change this value in January from 5% to 20%. Maybe you're expecting 15% in December and 10% in November. You could say okay, and then that would update your average annual soiling loss for the total year. Or you could just say input a single value and apply that for the whole year, which is what I'm going to do for this kind of simple first pass model. This next section down here is the DC losses section. This lets us enter in detailed expected loss values for a number of different electrical interconnection parameters. I'm just going to go ahead and leave everything as at default, but if you have more detailed information about a system that you are trying to model, you can go ahead and enter in those values yourself. Down here, we have options for calculating these total loss values a little bit differently, depending on if you have central inverters, microinverters, or DC optimizers. In this case, we're using central inverters, so we're just going to select this option right here. And then under our AC losses, so this is everything after the inverter, SAM has a default of 1% losses due to AC wiring. I'm just going to go ahead and leave that default. And there is an option for calculating sub-hourly clipping loss, but since we're doing everything in this model on an hourly basis, I'm just going to go ahead and leave that alone. There were options for transformer and transmission losses, which, again, if you have specific information on, you can go ahead and enter those with your specific values. But since I don't have that, I'm just going to go ahead and leave all of this as default. And finally, this tab right here is if you are calculating things based on a grid interconnection, which is really only relevant for the more advanced financial model and not relevant for Kotzebue in particular. So we're going to go ahead and skip that. So what we can do now is go down to this little button right here and click Simulate, and this will run our model. So you can see that all processed pretty quickly here. And SAM gives us a few of these default values here right off the bat. We can see our monthly AC energy production in kilowatt hours for the year that it simulates. All of this seems to look relatively good. We have a heat map of annual AC energy by hour of day and day of year. And then up here, we have our summary values, our total annual AC energy production, our DC capacity factor, our energy yield, specific to our total nameplate capacity, which looks like we're at about 1100, 1200, which seems reasonable. But the real special part about SAM is the really granular data that you can extract from the simulation report. So if we look here, we can see some summary statistics for on an annual basis. But what's really awesome is that we can get all of the data as a time series. And so this right here is hourly system power generated for the entire year. And we can go ahead and if we scroll down here, you can see there's all of these different values that get calculated. The one that we have selected right here is system power generated, but we could also say do our inverter efficiency, uh, DC clipping loss. And so we can see that this changes throughout the course of the year. We could select ground albedo, air mass, all these different values. And then it's as simple as clicking either send to CSV or send to Excel. And just like that, we have got ourselves an Excel value or an Excel spreadsheet with all of our hourly data calculated, ready to go. This next tab, we can also get monthly summary data, as well as single values. So these are total, annual. The next tab we have here is our calculated losses tab. This is really useful just for getting a sense of where losses are being generated in the system model. So we can see that these are all the ones that we entered over here in the losses tab. So we have 2% for module mismatch, 0.5% for diodes and interconnections, and we can see that reflected in our system losses, but we can also see the calculated system losses through reflection losses on the actual modules, in losses due to inverter inefficiency, inverter power consumption, all of that. We can see that we're also getting an additional 17.4% power generated from light reflecting off the ground and hitting the backside of the panels. Here, if you don't want to create plots directly in Excel after you export your data, you can come over here and create plots by default directly in SAM. You can plot out your time series data. And so this is the same data that you can retrieve from these data tables here, but you can see that you can zoom in and see everything by default right here. We can also go over to this Profiles tab, and this will allow us to plot monthly profiles for various outputs that SAM gives. We can select system power generated like before and see if we can get monthly outputs for that variable, but we can also add other variables onto the same plots to get a monthly view. We can also come over here to the Statistics tab, which is particularly useful, and we can see here that SAM automatically calculates summary statistics for all of the output variables, including mean, min-max, sum, standard deviation, average, daily minimum, average daily maximum, and this is just a good spot to pop into to check on some of these summary statistics if you don't want to calculate them yourself, or you just want to check up on the SAM output to make sure that everything looks more or less correct. And the last thing that I want to show on this results page is this heat map tab over here, which the summary page actually provides one for the annual AC energy right here, but we can actually generate heat maps for any of the output variables, which can be really useful. So, like I mentioned earlier, these show on the x-axis here the month of the year, and on the y-axis the hour of day. So it's a really good way to get a general visualization of the entire output year's worth of data all in one place. So we can only select one variable at a time for this. Right now, it's set to system power generated, but we could also set it to, say, our inverter AC output power, which should actually be pretty similar. but we could change it to something like our calculated GHI irradiance. We could look at some of the different weather parameters from the weather file. And an important note for any of these SAM output tables is you can always search for variables. So if we go up here and we search for, say, loss, for example, we could take a look at like the electrical bifacial mismatch loss. And so this is a really good way to see like where to see your seasonality trends for various loss parameters. So we can see that there's a lot of excess production in the spring, which is causing some electrical mismatch loss for the bifacial array towards more towards March and April. Same with inverter. Well, actually, not the same with inverter clipping loss. It looks like actually our inverter clipping loss is pretty good. Um, but this can be a nice way to, within SAM, do a lot of this data analysis without having to export it to something like Excel or Python and create those plots there. And so, with that being said, I'm going to go ahead and wrap up this tutorial right here. There are a bunch of other functionalities within SAM. You can really dig into some of the model inputs and outputs and generate a whole bunch of different particularly useful insights. So I would encourage you to really play around with SAM and also take a look at the documentation and user's manual, which will be linked in the description of this video. It's updated regularly and is a really wonderful resource for the really intricate details of how SAM works behind the scenes. I'll also provide a link to the user forums for SAM. The SAM developers are very active and very responsive to user questions, comments, and concerns regarding anything that you might find in SAM that you don't understand or think that might be behaving abnormally. So I would also encourage you to reach out to the SAM developers on the user forum if you have any further questions. I want to thank you for being here today and for going through this tutorial video with me. You can see here on the screen right now my contact info, so please reach out to me or members of my team if you have any specific questions about the modeling work that we did here today. And thank you to the Denali Commission and the U.S. Department of Energy Arctic Energy Office for funding the work that went into creating this tutorial. So thank you very much, and I will be signing